This is lab number 1, part 1, and I'm going to give a brief introduction on the digital voltmeter and how it works. So this is the typical voltmeter you'll find in the laboratory, one of a couple of varieties. They pretty much look the same. They have the same functions. So an AC voltage mode for measuring AC voltages, a DC voltage mode for measuring DC voltages, a fine scale DC voltage mode. Some of the other more advanced meters have both AC and DC millivolt voltage readings. An ohm measurement mode, so you can measure the resistance here. And finally, on this meter, there is a continuity tester and simultaneously measure the diode, so you can check the orientation of a diode and see which way is which by hooking it up to the meter. And if you hear a beep, it means you have got the diode directed in the right directions where current will flow. In other meters, there are two separate functions available for this. I refer to high and low inputs on some of the lecture videos. So the high is usually associated with the red label on the input jacks. These are banana jacks. And the low is either indicated by a black or COM. The common means it's the low. If you attach the COM to a ground, you have a grounded circuit. I don't recommend this in many cases, particularly if you're working on the bench, but sometimes it is necessary. There are a variety of ways you can configure the meter, in other words, attach probes. I happen to like using these adapters where they have banana connectors. They look like bananas on the bottom, those two pins, a plastic body with a little notch to indicate which goes to which connection, and then what's called a BNC coaxial cable connection. So you see one of them plugged into the meter. They happen to fit rather nicely. And you'll see one by itself alongside of the meter just to indicate what they look like. So the arrow, the notch always tells you which pin, namely the banana pin, is connected to the common or the outer shell of the BNC connector. You can't see in the photo the inner information line. There's a conductor in the middle of that shell. There's a Teflon tube basically that runs through that steel tube on the outside that's visible. Inside the Teflon cylinder or tube is another wire connector which mates with a pin inside the cable. I think some of these are shown in detail in the quantitative analysis electrochemistry videos. So these give you your orientation. They allow you to connect cables in a convenient fashion with little clips. And here's an example where I have a BNC cable connecting two voltmeters in the laboratory. So the reason I'm doing this is to show you that when you connect the meter to a device under test, and in this case the device under test is the meter on the right, you will actually see what the meter is doing. So both meters are in the voltage mode, and so it's trying to measure the voltage coming to it from the device under test. So both meters are trying to measure the voltage at the other end of the cable. And clearly, since there's no battery or power supply involved, there's no voltage. So this is what you would expect to see. The situation is going to change when you go to the resistance mode. In this slide, I've got the meter on the left trying to measure the resistance of the meter on the right. So the meter on the right is still in the voltage measurement mode, so it's trying to measure a voltage. As I mentioned in the lectures, the early lectures in this course, you want to have the voltage device, measuring device, to have an extremely high impedance or resistance so it doesn't perturb the actual circuit that you're trying to measure. And if you look at the resistance that's being determined by the left-hand meter, It's 11.12 mega ohms. That's a huge resistance. And to measure that resistance, it's applying, the meter on the left is applying a voltage to the meter on the right. So the meter on the right is then registering the voltage that's being applied to it by the meter on the left in the resistance measurement mode. If that sounds confusing, just realize that you're looking at the meters are trying to answer two different questions. The meter on the left is asking the question, what is the resistance of the object that I'm connected to on my right? The meter on the right is measuring what kind of voltage is being provided to me from the object on the left. I mentioned galvanometers in the discussions of the bridge circuits, and here is another galvanometer I have in one of the teaching labs, close-up photo. And this particular galvanometer, I discovered, has a little window over the moving coil mechanism that I describe in the lectures. So you can actually see that there is a moving coil mechanism. You can get a glimpse of the magnet, those little things underneath, but you can see how the thing will rotate back and forth. So here's a little setup with the galvanometer. I've got the meter of the DVM set to resistance mode. It's measuring the resistance, and it's going to attempt to measure the resistance of the galvanometer. And you can see from the deflection of the needle on the galvanometer that there's a current running through it. And note the polarity involved. So I've got the red cable attached to the right-hand input jack on the galvanometer. The red cable is the high regarding current flow and voltage on the DVM. And if you look at that galvanometer, you'll see that it's got roughly 2 divisions of current running through. Each division corresponds to 0.25 milliamps. So you can work out Ohm's law and determine that there's about 6 millivolts of voltage being applied to the current by the DVM. And Domino is back from Venice and her exploits in Carnival, which she will not speak about. Domino, however, has asked me to play around with the diode function, and you'll also notice in this particular meter there's separate continuity and diode measurement modes on this dial. So this is a slightly more expensive meter. So you'll notice here that I've got the meter in diode mode. I've got the same connection to the galvanometer. The amount of current passing through the galvanometer is larger this time. I can play around with the Ohm's law representation again, and I can see that I get roughly the same resistance value when I apply Ohm's law and the current and the voltage that's read off the meter. So 8 ohms as opposed to the 11 I got previously by directing resistance directly. So I reversed the connections here. I've got the red input cable on the left-hand side of the galvanometer's jacks. The needle is now deflected in the opposite direction. So this shows or demonstrates how the galvanometer, although used for measuring small currents, can give you the direction as well as a very sensitive level of sensitivity in terms of the current measurement. So a galvanometer is ideal for the detector in a bridge circuit. So in that little bridge section I have in the cartoons in the earlier lectures, this is the actual device you would put in there. And you could use this to measure temperature, temperature changes, gas chromatography detection, and so on. This also allows me now to fully establish that this particular jack on the DVM corresponds to the high, namely the high potential side. So the current is flowing from that jack out of the DVM for all these measurements of resistance and the diode.